GPS, or Global Positioning System, basically measures the transit time of a cleverly designed radio frequency signal from a satellite to a user receiver. There's really three segments to GPS. There's the ground segment, the control segment, made of 12 reference stations around the world. And these stations estimate the location of the satellites. Then the satellites broadcast that information together with their radio frequency signals. And then there's the user segment, which then does the trilateration. One of the limitations of GPS is that the signal power is very weak, a tenth of a millionth of a billionth of a watt. So that means it's easily blocked or altered by obstructions to the sky, for example, buildings. GPS is not reliably available indoors. Downtown Chicago, in urban canyons, what you may have is that the signals are going to bounce around, what we call multipath. And this is something we don't want for navigation. We want that for communication, but for navigation we want a direct line of sight to the satellite. How far are we to get a GPS that gets us good accuracy downtown? We're actually going the other way, where because the GPS signal is very weak, we're now experiencing more and more interference to GPS. So the availability of GPS is decreasing, especially in conflict areas, in Ukraine, in Israel, in Syria. So interference causes, loss of availability of GPS. But that triggers a lot of research, a lot of activity with new low Earth orbiting satellite constellations that are dedicated to navigation. Because those satellites are at low Earth orbit, they're closer to the Earth, they have much stronger signals, and they can now be tracked, more reliably. I'm Mathieu Joerger. I'm assistant professor in the Department of Aerospace and Ocean Engineering.